In this lesson, we are going to examine instruction set architectures or ISAs. When working with embedded systems, the choice of ISA is crucial since it exposes and hides architectural details, allowing a high degree of optimizations and a trade-off with regards to portability of code. Think about it this way. Choosing an ISA is kind of like deciding what to cook for lunch. The ingredients you choose and the way they are mixed determines what are you going to eat. Choose the wrong ISA for your task and you will never be satisfied. So we are going to learn how to choose the right ISA. As you go through this lesson, try to answer these questions. What is an ISA? What are the design decisions? What are its ingredients and how to mix them? And finally, what is unique about ISAs for embedded processors? Let's begin this particular lesson by taking a quiz of what these instructions are divided into. So here is a description of 3 different kinds of functionalities, and we want to name what kind of instruction it will be. So the type of instruction that would do this would be something which will deal with the data or memory access, such as a load or a store. Let's talk about the second kind of an operation, which is like making a function call or a branch. What kind of operation does this involve and what type of instruction would do this? So the instructions that would deal with the control flow of the program, such as branch and link instructions or jump instructions, would be the pertinent instructions here. And finally, there's a lot of processing which involves adding or multiplying values or subtracting them or dividing one by the other. What type of instructions involve those? Those kinds of instructions are called as arithmetic or logic instructions, which compare 2 operands and, for example, say true or false, or which add 2 registers and generate a result to be stored in the destination register and so on. So this table gives you a classification of the different instructions which do different kind of functionalities, which roughly could be divided into memory accesses or the ones which deal with the control flow, and the third one deals with the arithmetic or logic processing in terms of addition, subtractions, divisions, etc. So having understood the basics of the ISA design or the instruction set architecture design, now let's take a look at the design principles or the guidelines behind the ISA. So the first one is what to hide here is one of the biggest questions that need to be resolved in terms of the instruction set. We can expose a lot of architectural details or we can hide some of them, and that's a critical thing to discuss. So in particular, for our purposes, we are interested in VLIW or very large instruction word instruction set design in terms of what that instruction would be, what are the sub-instructions that could be there, and so on. And not only that, moreover, we are interested in VLIW for embedded systems, which is a different animal as we know, which is concerned with the energy consumption and so on. And so what's the most pertinent thing in terms of the VLIW for embedded processing? It is the encoding of the instruction set. So imagine that the instruction word could be either a 16-bit or 32-bit and so on, and a part of the word is used for registers, a part of it is used for opcodes and so on. And so depending on which bits are used and which bits are left unused, we have what is called as an instruction density, which decides the efficiency of this instruction as far as the energy consumption is concerned. If we have packed these bits, then we are utilizing them fully. If we are not packed them fully, then most of the bits are there, but they're not being used and they're just getting on and off and are wasting energy. So the higher the density is, the better. And so combining all these concepts about parallelism, the instruction density, and so on, we have what is called as a VLIW encoding, which is a scheme for generating the VLIW instruction set. So before we actually do the instruction set design and discuss the design alternatives and trade-offs, let's understand a few terminologies. The first term that we introduce is what is an operation? An operation is a RISC-like minimal unit of work, a smallest size thing that we want to get accomplished. So for example, we have shown here 2 simple operations which are RISC-like, and they are moving some constant values into registers as shown over here. So now what is an instruction? So a VLIW instruction is actually a fundamental unit of encoding. In other words, it is one which executes as one entity here. And it typically consists of multiple operations which execute in parallel. For example, here we have these 2 move instructions which could execute in parallel, and that constitutes one VLIW instruction over here. Now again, as I mentioned, VLIW is a really special type of an instruction. It is really very large and it consists of several sub-operations or operations which execute in parallel, such as these. And so many times how to fit that instruction into a word of memory is a question. And so VLIW folks introduce a new term here called a bundle, which is an instruction which lies on the memory boundaries, which is aligned with the memory. In our case, we have this VEX instruction set, and they call this memory aligned unit a syllable. So what is again a syllable? A syllable is an instruction which is memory aligned, which is designed to occupy one word of memory. So before we actually do the instruction set design and discuss the design alternatives and trade-offs, let's understand a few terminologies. The first term that we introduce is, what is an operation? An operation is a RISC-like minimal unit of work, a smallest size thing that we want to get accomplished. So for example, we have shown here two simple operations which are RISC-like, and they are moving some constant values into registers as shown over here. So now what is an instruction? So a VLIW instruction is actually a fundamental unit of encoding. In other words, it is one which executes as one entity here. And it typically consists of multiple operations which execute in parallel. For example, here we have these two move instructions which could execute in parallel, and that constitutes one VLIW instruction over here. Now again, as I mentioned, VLIW is a really special type of an instruction. It is really very large and it consists of several sub-operations or operations which execute in parallel, such as these. And so many times how to fit that instruction into a word of memory is a question. And so VLIW folks introduce a new term here called a bundle, which is an instruction which lies on the memory boundaries, which is aligned with the memory. In our case, we have this VEX instruction set, and they call this memory aligned unit a syllable. So what is again a syllable? A syllable is an instruction which is memory aligned, which is designed to occupy one word of memory. Let's look at the first statement. Most embedded systems are programmed at the assembly level, and the ISA design therefore matters to the end programmer. Is this true or false? The answer to that is false. It used to be the case that the embedded systems were programmed at assembly, but that was a long time back. With embedded systems becoming complex, they are no longer programmed at assembly level, but they are programmed at high-level languages such as C, C++, and the compiler then translates the code to assembly. So let us continue and look at the second statement. The ISA allows the designer to treat the processor as a black box. This statement is the reason for something called as the instruction set architecture to exist, and it is true. So the ISA allows the designer to hide the details of the processor and to be treated as a black box, and therefore the software doesn't need to worry about the details or doesn't need to even know them, what the processor is like below the hood. And the last statement now, understanding the ISA can help determine which processor to use for a given embedded system scenario. And this is absolutely true. As I was explaining earlier, the ISAs can be of compact instruction, the ISAs can be of dense instructions. The ISAs can be dense and compact instructions, and such instruction sets allow us to use these processors in energy efficient systems. On the other hand, if the ISA is not one of compact or dense instructions, it allows us to use the ISA for a general purpose computing purposes, and those systems can ignore the energy dimension and can focus on implementing the functionality of a general purpose computing system. So as we have been talking about, the ISA serves as an interface to the software, and naturally the question to ask is what to expose and what to hide. So taking the example of RISC processors, for example, in earlier versions of RISC machines, they exposed the delay slots. So why did they expose the delay slots? Because they wanted to give some control to the scheduler to schedule the instructions within a certain window so that they can get rid of some of those latencies. Secondly, many superscalers give an illusion of infinite number of registers to be available so that the updates to registers are instantaneous. Now, of course, this comes at a cost because you have to manage those registers and map them onto the physical registers, and you have to do things such as forwarding, scoreboarding, and finally renaming. So what are the peculiar things to be hidden or exposed in terms of the VLIW architectures? Remember, what is the key goal of VLIW? The key goal of VLIW is to be able to do static scheduling so that the parallelism is nicely captured in those multiple instructions that are scheduled in a given slot. So therefore, VLIW must expose the scheduler to the compiler. In other words, the ISA should be designed in such a way that it exposes the scheduling of instructions in those parallel slots to the compiler so that we can efficiently put the instructions as parallelly as possible. Contrast that with superscalars. That hides the scheduler because the scheduler is done in the hardware, and therefore the scheduler need not be exposed through the ISA. So in order to understand the scheduling issues in terms of hiding them versus exposing them, we had to dig deeper and look at the memory and the registers, which are critical parts of an architecture. So in modern architectures, the state of computation can be in two types of storage. A bulk of values are held in off-chip memory and they are not specialized. And a small set of values are held in fast registers and those are connected to the logic unit. Modern architectures not only hold these values in different places like in memory and registers, but they also separate the computation and memory access operations. So in order to further understand the implication of exposing the scheduling, let us understand what is the most important type of scheduling that is involved in all these modern architectures. So typically the sequential execution used to be the most primitive type of scheduling. However, invariably in all the different architectures that are present now, some kind of pipelining is being used to expose the parallelism in time. And so the first design choice that is present in pipeline architectures is the pipeline exposed? And is it exposed fully or is it exposed only partially? And those are the different design choices. On one extreme, we have completely hidden pipelines, and so the complete burden of scheduling falls on the hardware, such as using the Tomasulo's algorithm and so on. Now, this particular philosophy of having everything hidden leads to what is called as out-of-order execution, wherein the hardware is doing all the work using such algorithms as Tomasulo's. A second design choice is to expose at least some of the details of the pipeline, such as those in early RISC processors in which the delay slots were exposed. Using these delay slots, the schedulers used to be able to control the window in which the execution sits. So what is done in VRIW embedded processors? Well, the pipeline is exposed at this particular level of architecture or an implementation or both. So there are several variants of VRIW designs. So again, the pipeline is exposed partially or fully at different levels of details. For example, some VLIW designs expose the pipeline at architectural level or the interface level, whereas some others expose it even at a deeper level of implementation, which allows the scheduler to become even more aggressive. So we have been talking about scheduling as one of the key reasons for VLIW. Now let's test our knowledge of scheduling through a simple example and a quiz based on that. So a given simple code which is coming out of this simple excerpt here, which is translated into assembly over here as well as here, which of the following is likely to be a scheduled code? Assume that the loads take 3 cycles and all the instructions are 1 cycle. Please mark your answer. Is it the first one or is it the second one, which is likely to be a scheduled code? Not only you are going to give the answer, but you are also going to think of the reason why one of them is scheduled and the other one is likely not to be a scheduled code. The answer is that the second code is the scheduled code and not the first one. The reason is this add will keep waiting on the loads, the first and second load, and since their latencies are high, will keep waiting for them. Not only it will keep waiting for them, it will block the other load which is coming after it and so on. Whereas that is not true over here. All these loads are independent, so they can keep going because they are fetching all these different operands. They are going to different registers, so they don't get blocked, and that's why this is a better scheduled code than the first one. The first one in fact can be considered unscheduled because it is not really taking advantage of the fact that all these loads can execute in one after other in the pipeline, and the add gets enough time for the first loads to complete. And that is best explained by this dependence graph here. If you take the same sequence of instructions and put them after the other based on whose result is being used by which instruction, this is the graph that you get. You can see here that all these loads are independent of each other and they don't have to wait, so they can go first one after the other, followed by the add, followed by the sub, followed by the compare instruction, and so on and so forth. So you can see that by arranging the code in a top-down manner as given by this graph, one is able to put the good schedule on these instructions so that they take advantage of the latency and they also maximize the parallelism. So as seen in the previous beautiful example through the dependence graph, we have been able to figure out what is the implication of scheduling. What it really means is the notion of dependence and also the notion of independence. So in other words, in some cases, we can expose independence, and that can be used for scheduling instructions or operations in parallel. In some cases, we can expose dependence, and that can be used for scheduling instructions as well, the results of which are chained one after the other. Talking about VLIW, which is really a parallelism in space, we need to worry about one of these different issues. So talking about the issues of dependence and independence, they are the two sides of the same coin. Many times if we expose one, that is sufficient to resolve the other. So for example, if we expose the dependence information, we can figure out which operations that cannot be executed in parallel, and therefore we can pick the other operations and we can schedule them in parallel to take advantage of the VLIW. While that was true in VLIW, as against that, in superscalars, multiple issue is a feature which is simply absent, and so therefore no dependence information is exposed because we don't need to infer any instructions which can be scheduled in parallel. So in that sense, the superscalars is really a sequential architecture. Let us focus now again on VLIW, and VLIW is really an architecture of what we call as dependence and independence. So VLIW explicitly exposes multiple issue of instructions. In other words, multiple operations that can execute concurrently in a given clock cycle are explicitly put there in one long instruction. So therefore, the independent operations are encoded in a one long, large instruction. And in order for us to group these independent operations, one has to know that they do not have any dependence, and therefore VLIW is also dubbed as independence architecture. Remember that VLIW has no way of knowing whether two instructions are independent or dependent, and therefore it's the job of the compiler. So in order to better appreciate scheduling and dependence and independence, we have three architectures here which we are going to compare against different aspects. The first architecture is your familiar superscalar. The second one is data flow, in which when all the dependent operands are ready, the operation fires, generates a result, which in turn fires the other operations. That's data flow architecture. And the last one is VLIW, which we have been talking about, in which we have independent operations executing under a large instruction. So let us look at where the dependence information is captured and is presented to the architecture. For the superscalar architecture, the dependence information is implicit in the register names. In other words, all the dependencies are captured in the registers. In terms of data flow, the exact description of the dependence information is presented by presenting the flow, that which operands are used where and which operations depend on which other operations. Finally, for VLIW, the information which is important is independence, and that is captured in terms of which operations can go together in a large instruction and which are those operations which can execute under that large instruction in parallel. So in superscalar architecture, the information is exposed by the hardware control unit and is governed by it. In terms of data flow architecture, it is exposed by the compiler and is embedded in the program, is again governed by the scheduling of the program. And in VLIW architectures, this information is completely governed by the compiler and is implicit in terms of all those operations that execute under the umbrella of one large VLIW instruction. Going further, sometimes the dependence is explicitly expressed or exposed, and sometimes it is the independence that is explicitly expressed or exposed. So in terms of superscalars, the independence is exposed by the hardware control unit by finding out there are two independent instructions here that need to execute. In terms of data flow, again, it's a dynamic fact that some instruction will complete and its operands are ready, and therefore the intimation is generated by the hardware and independence is again exposed by the hardware. So in VLIW, on the other hand, the independence is explicitly managed and is controlled by the compiler because the independent instructions are statically decided and they are put together as a part of large one instruction. Now let us look at the effect of all this on the final schedule, that is when a particular instruction really executes. So where is that final scheduling done? As far as the superscalars are concerned, it is done by the hardware because that is the one which figures out a particular instruction is independent of the other and can now be executed. As far as the data flow is concerned, the readiness of a given instruction is again decided by the hardware because its operands are now available, and therefore it's again the hardware which decides it. Whereas in VLIW, the readiness of the instruction is statically scheduled and is decided by the compiler and is not under the hardware's decision making. And last but not the least, let's find out what is the role of compiler in terms of scheduling and independence versus dependence. So in terms of superscalars, what does the compiler do? The compiler rearranges the instructions to make the parallelism more evident and accessible to the hardware. For example, if an instruction shows in a particular window, then it is amenable to scheduling at the hardware level, and that is the role of the compiler to find out which instructions go in that window. In terms of the data flow architecture, it replaces some of the analysis that hardware would do, which would be extremely time consuming to be done at runtime. So for example, to decide that two operands are ready and their instruction is ready to go, that is the job of hardware. However, to make this connection between this instruction needs these operands and so on, that's the job of a compiler. Finally, in terms of VLIW, the compiler is the king. It replaces virtually all the hardware functions that would be dedicated to the parallelism exposure and scheduling. For example, it finds out the independence in the operations and schedules them as a part of the large, long instruction. Let us look at another aspect here in terms of exposure versus hiding things and the implication on scheduling. One of the important concepts here is called as hazards. So why does the hazard happen? It is because the registers and shared resources could be accessed in a non-deterministic manner, randomly by an instruction or group of instructions, and the read-write operations may leave undeterminable results in those places. So a key related concept here is the dependence. Let's revisit the concept of dependence by looking at this set of instructions that are in a pipeline. They execute as follows. First they are fetched, then they are decoded, then they go through execute cycle, determining the results. Then they do a memory operation if they are load and stores. And finally, they write their results back in terms of registers or memory. So here are these 5 instructions. Mark those which are dependent on each other. If none of them are, then don't mark anything. Please write your answers now. Coming back to this set of instructions, none of them are in fact dependent on each other because they are all writing to different set of registers. So in that sense, this was really a trick question. Did I get anybody here? Did anybody mark 2 instructions here to be dependent on each other? Because really none of them are, because they are again writing to totally different set of registers and accessing different pieces of memory. So they have no dependencies whatsoever. Let's do another quiz therefore, because the last one was really a trick quiz. Now this is the real one. Again, I have a set of instructions over here which are operating on different registers. And what they are doing is reading and writing values to these registers, operating in a pipeline such as this. And then let's answer these questions. Which instructions have hazards in them and which ones don't? Please check those boxes which have hazards and write your answers now. Let's look at the answers to this particular quiz. So what is going on in the first instructions? It is writing to register S2 in a particular cycle, and that will not occur until the 5th cycle, which is the write back cycle. So here is where the first instruction will write to S2 in the last cycle, which is the write back cycle. However, take a look at the next 2 instructions, AND and OR. What they are going to do, they are going to read the data from S2, register 2, before this 5th cycle. They are in fact going to do this reading right here in this particular execute cycle and so on. And so as you can see here, because of this out of order read of register 2, before its write occurs, the data hazard occurs in instruction 2 and 3. Now what about the instruction number 4, which is the add instruction? As you can see, it is taking the result out of register 2, combining it with the register 2, and then putting the result back in register 14. So there are 2 reads going on here for register 2, followed by a write to register 14. So as you can see, there is no hazard here between instruction 4 and instruction 1, because the instruction 1 would have written to the number 2 register, and then only the instruction 4 will read it from that number 2 register in its cycle, which follows after the write cycle. The last instruction we are going to look at is this store instruction. So what is going on over here? In terms of this instruction, we are writing to a location which is indexed from the $2 register here. And you can see that that write is occurring after the read is finished from the add registers, because you can see that the write back stage of the last instruction is far away from the read stage of the previous instructions. So therefore, there is no hazard between 4 and 5 as well. So the only two hazards which exist here are because of the first instruction and second, and because of the first instruction and the third. So again, talking about hazards, and we call them as structural hazards because they are a part of pipelining. The hazards are caused by dependencies, and the dependencies are of two different kinds, and so the hazards are of two different types. The true dependence, that is, reading a value after a write, causes an hazard, and if we don't do the read after the write has completed, then that's the question of an hazard, which is what we saw in the last slide. Now, why is it a very, very important issue? Remember speculation? So we are speculatively executing the instructions, and so sometimes we might be very aggressively scheduling them, because of which we might end up reading a value before the write is complete, and that is to be avoided. The second kind of dependence, as we know, is a false dependence, which could be a write after read or write after write kind of dependence. So the false dependence means there is no real flow of operands between the dependent instructions here. It is just that a particular resource is busy and it could not be overwritten unless the read from that resource is complete. The architectures hide the resources, especially in superscalars. And how do they get rid of this particular hazard then? It is removed by renaming the resource. That is, you have multiple software registers, and those software registers, even though they share the same name, could get mapped onto different physical registers, which is an act of renaming, and therefore we remove that hazard. Now, however, in case of true dependence, the hazard has to be carefully observed by the scheduler, which means that we cannot aggressively schedule beyond a particular point. Or if we have a very aggressive schedule, then the architecture has a mechanism to block an instruction before the read is complete. And for that matter, the hardware will have to keep track of whether the value has been written before it is allowed to be read. So let us look at more detailed examples of the hazards. In this example, assume that there is one memory unit and one integer ALU. A load instruction is taking 2 cycles and the mult instruction takes 4 cycles. As you can see that in these shaded regions, the hazards exist because the reads being issued before the data is available. So for example, between the instruction 2, which is writing the value of the load into R2, and the mult, which is using the value from R2, the hazard exists here because the load may not be complete. It is complete only in this W cycle here, and the reads for R2 are issued earlier. Similarly, the hazards would exist here between the instructions such as subtract instruction and the store instruction, because again, we are trying to write a value from R3 before the value could be completely generated by the sub instruction over here. Finally, a hazard would exist between the add and sub instruction, because add is generating a result in R4 and sub is using that result from R4, and the result may not be generated before it is requested from R4 by the sub instruction. So we saw that a bad schedule that would allow a read to happen before the dependent write has occurred would cause an hazard. But is that the only source? The answer is no. That's only one of the sources of hazards. The other reason for hazards is the resources, and it is called as resource hazard. So in other words, there is insufficient hardware resource to complete the request, because of which this read and write could occur out of order. What is an example of that? 2 load instructions cannot be issued at the same time because of the single ported cache, and therefore the loads cannot complete and could cause an hazard. Now, this is not really because of any dependence, but because the loads cannot parallelly operate because of a single ported cache, and it's an example of a resource hazard. So here is an example of a resource hazard. There is this first load instruction that happens to request the memory access in its 4th cycle over here, and then suddenly another instruction downhill in the schedule, instruction number 3, also kicks in, and that happens to request the memory access in the same cycle as this. We have a single ported memory, and both of these accesses cannot go through in the same cycle, and that's causing one of them to slow down and causing a hazard. We have talked a lot about hazards, but finally test our knowledge in terms of how well we understand these hazards through a quiz on the resource hazard. So in this example, check any instruction that will lead to a resource hazard. Assume that there is only one cache. We have different boxes here. check those two boxes which are going to cause the hazard. You can write your answers now. It should be easy to see that the kind of hazard or the resource hazard that will exist here will be because of the memory operations. So let's isolate only those operations first. And as you can see here, the only operation that would cause an hazard here would be the two memory operations that occur in the same cycle. And therefore, this memory access over here and that fetch from the memory which occur in the same cycle would cause an hazard. As you can see that in other memory cycles, there's only one memory access there, and therefore there will be no hazard present there except in this particular cycle. So scheduling is one of the key reasons to hide and to expose. But is that the only reason that guides the choice of ISA in terms of the design trade-offs? No, it is not the only reason. In fact, a trade-off exists between what to hide and what to expose because of a totally different reason. And that reason is really the compatibility. Remember, hardware is designed and it is exposed to the software, and the software keeps changing. So we want to keep this interface between hardware and software the same, and that is called as the compatibility between different generations of the software with regard to the hardware. Now, compatibility is the real choice that one would make in terms of what to hide and what to expose in terms of these design trade-offs. In terms of superscalers, the backward compatibility is very important. The architectures remain the same, the software keeps changing a lot, and therefore they need to be backward compatible. And in order for different generations of the software to evolve, the hardware hides all the details, the ISA hides all the details such as the issue width, latencies, and so on and so forth. However, embedded systems have a totally different life cycle. Typically, the hardware also changes within 2 or 3 years, and so the compatibility or backward compatibility issue is less significant or almost no significance in embedded systems. In other words, the VLIW compilers and programmers tackle the exposure and optimize the code very heavily to run on a specific family of VLIW, and that life cycle is over within 2 or 3 years, and then everything changes. The software changes, and so does the hardware. So therefore, there is no sense of compatibility in VLIW, and therefore this trade-off is absent in terms of what to hide and what to expose, and everything is exposed that is specific to the architectures in VLIW. Summarizing this big discussion about scheduling, hazards, what to expose, what not to expose, let us summarize this in terms of the VLIW design principles. So VLIW ISA design principle consists of exposing parallel operations, because the compiler can take advantage of it and could schedule the parallel instruction. Who must guarantee the safety of those parallel operations? The compiler must guarantee the safety of those parallel operations. What does the safety of parallel operations mean? That means that they should not have any dependencies and they should not cause any hazards. You may ask me, so why is the compiler in charge here again? Let's remind ourselves, VLIW means simplification of hardware. So if we take away certain mechanisms such as hazard detection from the hardware becomes energy efficient, and that is the key goal of embedded processors. Second thing we talked about is the life cycle of embedded systems. So the life cycle of embedded systems is a short one, typically 2 to 3 years, wherein a specific hardware and software both change. And so therefore, exposure is a specific implementation. And once that implementation changes, everything will change. So in other words, everything that is needed should be exposed for efficiency. What does that mean? Specifically, latency, function units, the resources, their guarantees, their constraints, all are visible to the compiler. You can see that these are very implementation specific details, and by exposing those, compiler can take advantage of them statically and by keeping the code as optimized as possible. The compiler is to be trusted, and we put the complete burden on making sure there are no hazards and so on compiler. And therefore, hardware is very, very simple. And finally, not everything is exposed because there could be some weaknesses too in the hardware. For example, there could be only one unit which will be doing certain activity. And that's typically exposed through a constraint, and not by mentioning that there is only one such resource over there. So in other words, certain weaknesses are simply transmitted as constraints and not really exposed as number of resources. Quiz time. So we have 3 statements here. Please put check marks in front of those which are true. The first statement, VLIW's advantages come largely from having an intelligent compiler that can schedule many instructions simultaneously. Second statement, VLIW compatible code is easily portable to hardware other than the chip for which it is designed for. And the last but not the least, VLIW also has some problems with the inflexibility of its compiler first design solution space. So the first statement, VLIW's advantages come largely from having an intelligent compiler. Absolutely, this statement is true because as you can see, the biggest strength of VLIW is the compiler. The second statement, is VLIW code portable? The answer is absolutely no. VLIW code is very custom, it's highly optimized for the chip, and therefore if you port it to the other chip, it's not going to execute properly. In fact, it could be hazardous. And so finally, this is a matter of opinion, but does the VLIW has some associated set of problems because of its complete reliance on compiler first design? Absolutely. VLIW has some problems, especially the lack of portability is one of the key problems of VLIW. And the second problem is too much reliance on compiler. So the compiler is less than super perfect, the code quality is poor, and the code could be quite slow. So earlier we saw how the VLIW is very much dependent on the compiler ability to parallelize the instructions. So let us take a simple quiz to find out where we are and how well we understand the parallelization of instructions. So the question is, we have two instructions here. The first one is a store, the second one is a load. And the question is whether these two can be executed in parallel by a VLIW compiler. The choices are, yes, they can be run in parallel on a VLIW processor. No, they can never be run in parallel on a VLIW processor. And the third choice is, it depends on the data. Please go ahead and mark your choices and then we'll look at the answers. And the correct answer is that no, they can never be run on parallel on a VLIW processor. What is the reason behind it? The reason behind it is very simple. Let the value of $2 be equal to 4 and let the $5 be equal to 0. And so if that is the case, then these two instructions point to the exact same memory and you are writing into that memory and you're reading at the same time, which is not allowed, and therefore they cannot execute in parallel. Now you may ask us, so why can't we decide on this that these instructions can be parallel or they cannot be parallel? Statically, when the VLIW compiler analyzes these two instructions, it doesn't know the value of $2. It also doesn't know the value of $5. What are these? These are actually the offsets from these different locations. Using the conservative estimates, $2 is equal to 4 and $5 is equal to 0, the compiler is able to say that, okay, these two are dependent under certain circumstances and therefore it will not parallelize it. In case of superscalars, it is possible to parallelize it dynamically because we would know what value $2 has and what value $5 has. Statically, however, it is not possible to know this. The VLIW compiler operates statically and therefore it will rule that these instructions cannot be parallelized. So let's take a high-level view of how a VLIW compiler operates. So as you recall, the VLIW is all about independence. That is, the independent instructions execute together. So the first thing that a VLIW compiler does is gathers the independent operations and bundles them into instructions. Assignment into bundles or different operations to be a part of the same instructions involves something more. Since the architecture does not have an ability to detect and resolve hazards to keep it energy efficient, the compiler must do so, and so the second responsibility of the compiler is to resolve the hazards, resource and structural hazards, to be able to schedule those instructions in the same slot. Finally, the instructions are scheduled, but what about their operands? Well, most of the operands must reside in the registers because remember, individual instruction is a RISC instruction, so it needs operands in registers. Since VLIW has such a large number of function units, the registers are also split into different clusters, and the operands are allocated to registers which are in different clusters, and we generate references to those different registers. Now that's the third and most important part of the VLIW code generation. So the discussion that we had on an earlier slide exposes many issues here. There are two important issues which are exposed in the pipelines in terms of scheduling of operations and assignment of operands and hazards. The first set of issues deal with the horizontal issues, that is the decisions within the instruction word. As you know, there are multiple operations sitting within an instruction word and how these issues affect those different operations which concurrently execute is the first thing that we are going to see. And the second thing that we are going to see is how these decisions operate across different instructions, different large instructions, which are one after the other in the schedule. And those issues are classified as vertical issues. To understand these issues on the horizontal side, let's take a look at the different VEX instructions which are scheduled as follows over here. The same schedule is shown here in terms of VRIW instructions. As you can see here, in the first slot, there is an assignment to a register R0.1, and in the same execution, there is an assignment to R0.2 of a value of 2. This is all fine over here, but let's take a look at what happens in the next slot. Alright, so after the first instruction executes, then the second one executes sequentially after that. What happens in this particular process? This value 2, which is sitting in R0.2, gets transferred here. And when this instruction executes, that value is copied from R0.2 into R0.1. But guess what else is going on simultaneously here? Simultaneously, we are copying a new value into R0.2. So the real question is, which value is eventually going to show up in R0.1? Is it going to be 2, which is going through this route, or is it going to be 3, which is going through this route? In most VLIWs, the answer will be R0.1 will contain 2. This is so because the old value will be first read, then only the new value will be written. All the reads are to happen before any of the writes happens. What is the other question that we face in the horizontal operations side? Well, the other question is, what about exception? What is an exception? An exception is maybe division by 0 is one example of that. A particular value is divided by 0 and it is an undefined result. In case such an exception occurs in one of the instructions, what happens to the second instruction? Are both of them retired and none of them is processed? Or is it that the only one which has the exception gets thrown away? Well, it depends on an architecture. In many cases, if the instructions are interdependent, the VRIWs take an approach of just discarding both of them. And so the exception is treated as a global exception which spans both of these instructions. So that was a glimpse of what are the different issues as far as the horizontal model of execution is concerned. Now let's take a look at the vertical issues. Well, what is a vertical issue? The vertical issue is across those pipeline instructions or across the VRIW pipeline instructions. Remember, in VRIW architecture, the pipeline latencies are exposed to the compiler. Why are they exposed? That way, the compiler can heavily optimize the code, filling the delays. But what is a delay? Well, delay is because of getting the operands from the memory or because of branches and so on. If you go to the memory, the delays from getting the values from memory could be variable. This could be because of the cache hierarchies and so on. The compiler understands the maximum latency over here. What is a maximum latency? The amount of cycles it takes to get that operand from the deepest memory hierarchy here, such as from the memory which is main memory or from even a disk. So to understand the vertical execution model, consider a load operation which is trying to get a value from the memory. Now this is a variable latency operation. So what happens if the operation completes before its maximum latency? So the first model is called as equal to or EQ model. What does it do? It stalls the instruction until the assigned latency expires, and so the load completes only in a fixed number of cycles which is equal to the maximum number of cycles. Well, what's the problem with that? There will be a problem in processing the exceptions because we have this load which is completing in a maximum number of cycles, so no cycles are left for handling any problems about accessing the memory. Apart from exceptions, this is also an inefficient model because you are unnecessarily stalling even though you have values in hand. The second model, as one could imagine, is less than equal to model. So again, consider the same load. What may happen to that load? If it gets the value from a cache, it may complete sooner and it may complete in fewer cycles. Now this is a very efficient model because the latency is less than what it could be. This is a better model for handling an exception. Why is it so? It is so because you have those extra cycles in hand. What can we do with those? We can use those extra cycles for propagating the exceptional value. That is, for example, we try to access a memory and it caused a fault and we are not able to get a value from that memory location for whatever reasons. We can immediately communicate that to the dependent instructions and cause an exception to occur on those instructions as well. And therefore, the exception handling becomes very efficient and also precise. Having seen the differences between an EQ model and an LEQ model, let us now test our knowledge of these differences. So here is a simple quiz to test our knowledge of the execution that occurs as far as EQ is concerned and as far as LEQ is concerned. Please mark those responses which execute under EQ model as E and the ones which execute under LEQ model as L. So the first statement is, register values don't change until operation completes. Is it an L or is it an E? The second statement is, it simplifies instrumentation of precise interrupts. Is it good in EQ or is it better in LEQ? The third question is, can reduce the operation latencies and maintain source code compatibility. Is it E or is it L? Okay, the fourth one is, can't reduce operation latencies and maintain source code compatibility. Is it E or is it L? The next one is, reduces register pressure because source operations stay around longer. Is it true in E or is it true in L? And finally, the destination register contents become unreliable immediately. Is it true in E or is it in L? Please go ahead and mark these responses as appropriate for each of these boxes, and then we'll visit the answers. So let us start with the first response here. The register values don't change until the operation completes. Is it true in EQ or is it true in LEQ? So you can see that this is a EQ model because it takes those many cycles to complete, and the register values cannot complete and many those cycles elapse, and therefore it depends on the completion of the operation. The next statement, simplifies implementation of precise interrupts. Is it true in EQ or is it true in LEQ? Obviously it is true in LEQ because the interrupt becomes immediately effective once the operation completes without waiting for extra cycles. Now, what's the problem with waiting for extra cycles? Well, during those extra cycles, some other activity might complete, and therefore you might have to undo that activity to process that interrupt. And that's the complication. The next one, is it EQ or is it LEQ, which can reduce the operation latencies and maintain source code compatibility? Well, the answer is LEQ. Why is it so? Because if the operation, such as the load, can complete earlier, we get the operands in those registers right away, and therefore the other instructions can proceed. Now let's look at the reverse of this particular statement. Can't reduce the operation latencies or maintain source code compatibility. Is it EQ or is it LEQ? The answer here is EQ. Why is it EQ? Because even if the operation is somewhat completed in earlier number of cycles, it stalls and it doesn't commit until those many cycles elapse, and therefore the values will not be seen in those registers until that particular latency is completed. Now what is the second part here? Not being able to maintain the source code compatibility. Well, imagine a case of debugging in this particular case. And what is going on here is we are stalling the commit of these registers until those many cycles are completed. So what happens in this particular process? Some other operations may complete and those values might show up as committed. So in that sense, it is occurring slightly out of order because of the stalls that are introduced under LEQ model here. What about register pressure? That is, demand for registers at a given execution point in the program. Which model reduces it? Is it EQ or is it LEQ? Well, the answer is it is the EQ model which reduces the register pressure because the source operands stay around longer. So the longer duration of the operand staying, how does it reduce the register pressure? Well, because that operand is available for longer in the original register, it can be reused by many instructions before it goes away, and therefore many dependent instructions can execute on that particular register. Finally, what about the destination register contents? Do they become unreliable immediately in EQ or do they become unreliable in LEQ? Well, the answer is obvious here because LEQ updates the destination register as soon as the latency is completed without waiting for the complete latency. The destination register is updated and therefore it is no longer available for the source values. So in other words, under LEQ, the register updates happen right away, and that's why those could become unreliable as far as the pending instructions are concerned. Under this model, therefore, we need to worry about the hazards in a very subtle way, because an instruction which is completing sooner than is the maximum number of cycles could pose a hazard if there are other pending instructions which are on that particular register. So far we have looked at the scheduling issues, and then following that we looked at the different horizontal versus vertical execution model issues. Now let's turn our attention to one of the last important parts over here, which is instruction set encoding, which is very critical in terms of the code density and so on. Why is encoding such an important asset? Well, on embedded systems, if you don't encode well, you have those extra bits which keep flipping, which do not contribute anywhere fruitfully towards the execution. On the other hand, they waste energy because every switching activity causes an energy drain. So the encoding should be flexible on one hand to be able to accommodate different needs for instruction sets, and on the other hand it should be compact so that it doesn't cause unnecessary wastage of energy. So let us test our knowledge for the encoding via a simple quiz. We have shown here multiple such possibilities, and what we want you to do is mark those instruction encodings which are fixed as F, the ones which are variable in terms of length as V, and the ones which are somewhat fixed but could also be flexible and variable as hybrid or H. Let us look at the first choice. So what do we have here as the first choice? We have an instruction which has the operands, and the operands could have an address specifier and address field 1, and it could have multiple numbers of operands. It could have another operand which has another address specifier and address field. The second choice here is, in this particular instruction, we have an operation or an opcode. We have an address field 1, address field 2, and address field 3. So no matter what we do, we have 3 fields here. As against that, in the first one, sometimes we could have just 2 fields, sometimes we could have 4 fields. And finally, we have the last choice here. This instruction could have a field of 3, or there could be an alternative which has a field of 4, which could have address specifiers and so on here. Go ahead with this explanation and mark what you think is V or F or H. Mark your answers now. Well, let's take a look at the first one. As I mentioned earlier, this particular instruction could have 2 fields or could have 4 fields depending on the need. And so the length of this particular instruction could vary, and that's why it is a variable encoding instruction. What about the second instruction? The second instruction, on the other hand, has fixed number of fields. It always has these 4 fields over here, and it is easy to see that this is a fixed encoding format here. Finally, we have a third type of instruction which could have 3 fields as shown over here, or which could have 4 fields, and those are the only 2 formats this instruction comes in. So in other words, this instruction can be 3 wide or 4 wide over here in terms of number of fields, and therefore it's a hybrid. It is not as flexible as the variable length instruction, and it is not as inflexible as fixed set. It can go between either 3 or 4. So what are the advantages and disadvantages of these different choices of encoding? You can see that the first choice offers a lot of flexibility because we could vary the instruction length from 2 to 3 to 4 to 5, a lot of flexibility here. The second one has 0 flexibility because the length of the instruction is always fixed. However, the third choice has somewhat of a flexibility because the length of the instruction could be 3 fields or 4 fields, but it cannot vary arbitrarily to any number of fields. So that is as far as the flexibility is concerned. What about the code density? Well, you can see that the best code density is achieved in the variable length format. Why is it so? Because we are able to vary the length of the instruction as per our needs. So we are not putting any extra bits there whatsoever. In the second case, the number of bits are fixed, the number of fields are fixed. So no matter what will happen, we'll always be flipping those many bits. And so the code density could be very poor if we end up just using the first 2 fields and leave the other 2 fields empty. We could address the code density issue somewhat in number 3 because we could keep the number of fields to be 3 or 4 and keep it as compact as possible, but not entirely as flexible as in V. So you may ask me, why not just go for V? Well, variable length instructions are very difficult to process in terms of the hardware, and that's why they are not really preferred. In fact, there are no processors, practical processors, which really have those. The fixed length is the most common one, and then the next best alternative is the hybrid one. Alright, having introduced the different encoding schemes in terms of fixed, variable, or hybrid, Let us see for some practical processors now what kind of encoding schemes are followed. Well, one of the largest class of such processors is DSPs. What are DSPs? DSPs stand for Digital Signal Processors. DSPs are one of the most important classes of processors. They are used for noise cancellation and shaping up the signal in our cell phones and smartphones. So what kind of encoding the DSPs use? Usually they are of fixed length, but they may do multiple actions during one level of encoding. For example, one of the most common operations in DSPs is called as multiply accumulate. So this multiply accumulate instruction will trigger multiple activities. It will go to the addressing unit, it will fetch those operands, it will go to the multiplier, multiply those operands, and then finally it will do an accumulation operator in a particular register. Due to this encoding, which is fixed, however, it can introduce some difficulties. For example, it can complicate certain optimizations. For example, the operations get split off across different instructions, and in TI C54X, for example, certain optimizations become very difficult. In general, the code optimizations and efficient code generation becomes a challenging problem for fixed encoding, especially in DSPs, and DSP code optimization is really an open challenge. Later in this course, we are going to see very important and interesting DSP optimizations. What is the other important class of processors that are used in embedded computing? One of them could be a vector encoding and vector processors. Much of the media processing could occur as a vector processing. There's a lot of data, and so there is a single vector instruction, but there could be a variable number of operations it could do depending on the number of data items it processes. And so this is called as one variable flavor. So how does this really work for vector machines? Well, you have all these different media instructions. They're sitting inside the loops, and the compiler finds out effective loop analysis and transformations to get all these different operands into these instructions and vectorizes the code. So what are the different kinds of loop analyses and transformations? Well, they're called as loop fusion. That is, we are taking different loop nests and putting them together inside one loop nest. And the second important one is called as unroll and jam. In this particular case, what we do is we take a loop and we unroll it, and thereby exposing all these different operations that can go in one instruction. We can bundle those operations into one instruction and then use this one variable encoding. Alright, having seen the different types of encodings, now we look at a nice summary of what happens in terms of the number of runtime operations versus the type of encoding. And we are going to do this for three different kind of architectures. Again, RISC. The second one is DSP. The third was VLIW, and in fact we are also going to do it for vector. Let us look at the single encoding and RISC architecture. So you typically have such architectures when there is a single simple instruction, and so it results in a single runtime operation. What happens when you have a single encoding? We have a variable number of such operations in DSPs. What does that mean? This means that such a single encoding results, although in a fixed type of instruction, the number of such operations within that instruction could be variable, and that happens to be the case in DSPs. Why is it the case? Because DSPs typically generate lots of different kinds of operations even through a single encoding, such as getting the operands, multiplying them, adding them to the accumulator, as what happens in the multiply accumulate instruction, for example. Now in terms of the vector processing, the encoding is single or fixed. The number of such operations become dynamic because in vectors you have multiple operands, and each of those operands could do different operations. So in SIMD case, of course, they do all the same operations. In case of others, there could be other kinds of operations, and the number of such operations would depend on the vector length, the data length, and that is why even though the instruction is fixed, the data length could vary and the number of such runtime operations could also vary. Now things are a little bit more complex as far as the variable instructions are concerned. Variable, I mean by that variable encoding. Variable encoding is applied to RISC, especially when the RISC instructions are compressed. And that's the primary reason why we have the length of instruction varying. Because in RISC, depending on the level of compression, the length of the instruction could vary. Even though length of the instruction varies because of the level of compression, the number of operations is still fixed. Typically, it's just a single operation in such instructions. let's look at VLIWs. So in VLIW, the primary reason for variable instruction encoding is the number of slots that are there. So some instructions could have 3 slots, some could have 4, and so on. And by that I mean the number of slots which are filled with the ready to execute operations. And because the number of slots vary per the length of the instruction, the number of operations also vary, and therefore in VLIWs we have variable number of operations at runtime for variable length encoding. Finally, let's go to CISC. So what happens in CISC for variable encoding? Well, there are 2 things which are going on. For a given instruction, for a different addressing mode, we will have a length of the instruction different. Now, depending on the type of encoding and the addressing mode, the number of operations could also vary. So not only it is changing at runtime, not only it is variable, but it's also dynamic. That is, it could be different for different instructions. So this table is a very interesting and important one for you to understand the differences between the encoding versus number of operations. So now, let us summarize what we saw in the last slide in terms of what we call a summary of encodings. As you know, there are 2 sides to it. One is the fixed versus variable in terms of the length of the instruction, and the second one is the number of operations, whether it is static, whether it is variable, or whether it is dynamic. So what does the first word refers here in terms of variable length encoding? So it refers to the different types of encodings. That means the number of such instructions which are sitting there in one large instruction could be variable as against fixed. So the word variable refers here to the instructions in terms of whether they are fixed encoding or variable encoding. Typically, when we talk about the encoding, we also talk about not just the length of the instruction, but the number of operations. And so the second word that refers to in characterization of an instruction is whether it is static or it is dynamic. So in this particular case, the word dynamic means that the number of such operations which are sitting in an instruction is going to be dynamic or is going to be determined at runtime. Let us look at an example here. For example, in CISC instructions, which are complex instructions, which have multiple operations inside them, they are variable length. What does that mean? There could be the length of the instruction could vary here from 16-bit, it could be 32-bit, it could be a 24-bit, or it could be even some odd number, or it could be a 64-bit instruction. So the length of the instruction varies here. That's what this first word says here. Not only it says that, the second word says that the number of operations that are done by this particular instruction could be dynamic. In other words, it could fetch 2 operands, multiply them, add them, and so on. So there may be 4 operations here, 2 for fetch, 1 for multiplication, 1 for addition. Or depending on the addressing mode, the same instruction could in fact go to the memory twice. So there could be 3 memory accesses here, maybe followed by a multiply and followed by an accumulate. So in short, this CISC variable dynamic really means it's a variable length instruction, and the number of runtime operations is dynamic. It changes from an instruction to the other, and it varies at runtime. Alright, another example of this CISC instruction could be a string move. What does it mean? A whole string is being copied from one area to the other in memory. So depending on the length of the string, number of memory operations here is obviously variable. Now depending on the number of operands that are being copied, again the number of fields could be different. So therefore the length of the instruction could also be variable. And so this is a classic example. A string move is a classic example of an instruction which has variable length in terms of encoding and which is also dynamic in terms of the number of runtime operations. Having seen 2 different dimensions for instruction encoding, which is the instruction length and the number of runtime operations, now let's take a specific look at the instruction encoding issues for embedded processors. For that matter, we are going to focus on the VLIW because that is the chosen instruction set format for most of the embedded processors. So what are the issues here? Well, as you can easily imagine, because the VLIW instructions are especially very long, the encoding is going to be a very critical issue for them. In other words, the length of the instruction otherwise will become humongously long because of the nature of the instructions being quite long. And so, compaction and clever encoding ways are very, very, very important. And so the real question is, how do we reduce size for the VLIW instructions? There are many advanced techniques which we are going to visit step by step. But even before we talk about advanced techniques, we can do something simple. And that is getting rid of those no-ops. So we had two types of no-ops. There are vertical no-ops due to exposed latencies. For example, because the result of a load instruction is not going to be available for next 3 or 4 cycles, we are going to have to put multiple no-ops there. So how do we address this no-ops? Well, instead of having those no-ops sitting for lots and lots of cycles and those unoccupied slots, which is a wastage of the space, we could have a multi-cycle no-op directive. So for example, there could be a special instruction which is just generating those multiple no-ops which could execute for multiple variable number of cycles. Now here is an example of encoding which is fixed in terms of the length, that it is a simple no-op instruction, but which results in multiple variable operations dynamically, such as the number of such no-ops that are generated at runtime will vary. As you will see later in the class, lots and lots of no-ops are generated by the compiler because it is unable to find enough parallelism to fill those VLIW slots. And so this results in lots and lots of horizontal no-ops in the code. So how do we deal with those? We can encode those by using what is called as a start bit and a stop bit. In other words, wherever we have those no-ops, we'll say there is a start bit which says that it has 3 no-ops or 4 no-ops, and then they will put another bit to tell us where it stops, and the number of such bits can tell us the number of no-ops. So in other words, we have captured each one of those no-ops through a single bit. To appreciate the role of encoding and compaction, let us take a look at a typical VLIW code that is generated and see how the variable length encoding is going to help us do the compaction. So here is a VLIW schedule or the code that is generated on the left hand side over here by the compiler. What you are seeing here is there is an active instruction which is not an no-op, which is present in slot number 1 and the last slot. Then in the second cycle, we do have such an active instruction, but only one of them is present over here. And in the third one, again, we do have only one active instruction here. So in other words, you can see there are lots and lots of no-ops which are indicated by white spaces over here. Now, if you have fixed encoding, you're still going to have a very long instruction. You can see that only 2 out of 4 slots are going to be occupied here for the first one. For the second slot, as you can see here, only 1 out of 4 is going to be occupied. So in other words, 75% space is going to be wasted. For the third one, again, only 1 out of 4 is going to be occupied, and so on and so forth. So if you have fixed encoding, you are going to waste a lot of time. However, this is how things are going to look under variable length encoding. So here is the first instruction here with 2 bits attached to it. The first one shows that this is an active instruction, and the 2 bits tell us that this is really a no-op that is going to sit here. And so we can compactly encode this as one simple instruction. The next one is going to be another active instruction, and attached to that is one simple bit which is indicating the no-op. So what it tells us is this instruction is going to have A followed by 2 no-ops. Following that we'll have B0, and then we'll have another no-op. So this is how it translates over here, that we have A0, 2 no-ops given by those 2 stop bits. Then we have B0 sitting there. That takes care of the first instruction. So this becomes first VLIW instruction. Following that we have another no-op, but that spills over to the second VLIW instruction, and that gets generated. Following that you can see that we have C0 here, which is an active instruction. That goes into the next slot here, shown by this arrow. And following C0 we are going to have 3 no-ops, which is indicated by 3 bits here. And so we go ahead and generate 1, 2, and 3 no-ops over here. Finally, we do have D0 here, and that goes over here as an active instruction. Following that, we do have 2 no-ops. Those get generated here. Following that, E0 is there, which gets generated as an active instruction. And then we do not have any such no-op here, and that is getting generated as an empty slot here, and so on. So we can see here that having an active instruction followed by 2 bits allows us to very compactly encode this no-op in pretty much the space that we have for an active instruction plus 2 bits. However, the number of such instructions, if they have lots and lots of no-ops, become variable in terms of their length. A lot of them become variable. And so this instruction format allows us to do very compact encoding, but is also a variable length instruction format. Alright, let's look at some important encoding techniques for VLIW through examples. and we're going to look at what is called as a fixed overhead encoding. The big idea was to take the VLIW instruction, get rid of all the no-ops, but then also add a mask which has bits to tell us which of those active instructions goes in which slot in the expanded version. Let's take a look at the example now. So as you can see here, this is an example of a fixed overhead encoding. Here are some active operations which are not no-ops which are present here. But in addition, you also have this mass and also the PC increments. Now let's look at how this works. So what happens is the mask is used for the instructions which are following it, and the mask tells us which instruction goes where. For example, the first mask is 101001111, and it applies to all these instructions which are active instructions which are sitting here. Tells us that the first instruction goes into the position 1 over here. As you can see, it's shown by this arrow. This W00 goes into the first slot over here. The next one is 0. That means there is a no-op here. So no-op will get generated here. The one after that, which is W02, will be occupying the third slot here, as shown by this masked 1 over here. Again, there are two no-ops following that, as shown by these two zeros over here. And then we have 111, which applies to the other instructions which are present. W05 goes here in that slot, W06 goes here, and finally W07 goes here. And as you can see, after all these instructions are mapped such as this, the instruction buffer is generated and it's sent to the decode unit, and it will treat this as a VLIW instructions with these no-ops generated. You can see that a good amount of compaction occurred here. Why? Because we are keeping track of only the active instructions, which are W0, W02, W05, W06, W07. So there are only 5 such instructions which we have tracked. In addition, we have paid a slight overhead here for keeping this mask, which tells us the mapping of these as the instructions get expanded. We also have here a PC increment, which is noted sometimes as a part of this encoding scheme. What does it tell us? It tells us where is the next PC address where the new instructions could be found. As you can see here, after generating this instruction, the PC will be incremented by whatever is this offset here. That's where the next instruction will get generated. And what will be that next instruction which is getting generated at the next PC address? That is going to be told to us by this mask, and again the active instructions that are following. So this will be that active instruction which is sitting at the next PC address. Again, W12 as per that mask will get mapped to the second location because of the second bit is turned on here. W14 will get mapped at the fourth location, and so on. And you can see that a whole bunch of no-ops are again getting generated because of these zeros here. So as you saw from the previous example, we have the compacted instruction which consists only of those active instructions and a mask, and it also tells us where is the next PC address based on the increment. How is the increment determined? You can see that easily the increment is determined by noting the number of active instructions there. So what are the advantages and disadvantages of this particular scheme? The advantage, as you can see here, is simplicity. It's a very simple scheme which keeps track of only the active instructions and the mask and carries out the mapping using the mask. What is the disadvantage here? Well, you need the mask. So this has a space overhead, and that space overhead is fixed. You can see that the length of the mask is fixed and it is dependent on the length of the VLIW. So for very long VLIW instructions, this scheme might have some disadvantages. So having seen the fixed encoding scheme and its disadvantages, now let's look at the distributed encoding scheme and how it removes those disadvantages. So the fixed overhead of maintaining the mask is removed in this particular case, and the overhead is variable. What does a variable overhead mean? A variable overhead means that we keep paying different amount of encoding overheads for different lengths of instruction. The longer the VLIW the instruction is, we pay a higher overhead, but if it has shorter or less number of no-ops, we pay lesser overhead. This scheme involves putting a stop bit as a delimiter. It has distributed an incremental encoding cost, which means that the encoding cost is spread across different instructions, and you pay only incrementally. That means if you already paid a lot of cost for a previous instruction, you pay less cost for the next one. The scheme is a little bit more complex. It's good that it does not have a fixed size mask. You can see that it has only those bits which it needs to for creating those no-ops. So depending on the number of no-ops, we pay the penalty of overhead. That's why it has a variable overhead. And then the other thing there is no need to compute the next PC, because as we are going through the instruction, we are done with the complete instruction. We using the start bit for the next instruction, we start the next instruction. So what's the catch here? Why is it that we even have this fixed size encoding? Why is it that this scheme is not adopted if it is so good? Because it has all these advantages. It has overheads proportional to the number of no-ops, and there is no need to compute the PC address. Well, the catch is that it needs much more complex decoding logic. Because see, what is going on here is that we have all those bits embedded as a part of the instruction. And so it is not a matter of generating the instruction, but it is a matter of decoding the existing instruction. So what we have really done here is encoded all those no-ops through those bits. And so during the decoding process, we are going to need more complex machinery now. There has been an actual implementation of this encoding scheme in the Texas Instruments C6 family, and the idea there was to also add a parallel bit to generate all these different masks or no-ops in parallel. Having seen two different schemes, the first one being fixed overhead encoding and the second one being variable overhead encoding or a distributed encoding scheme. Now let's take a look at a mix of the two, which is called as the template-based encoding scheme. So this one allows you to do some encoding, but not at the cost of a complex decoding logic. So what is this scheme about? The scheme is all about keeping some types of templates for allowing certain types of mappings and allowing some bits for certain type of operations to be mapped into some places. So this has relatively low overhead because you can use those templates and you can keep the encoding compact. Another advantage is there is no penalty for short instructions, unlike the fixed overhead encoding, in which you have to keep that mask even for short encodings or short instructions. So what's the catch here? The catch is we have only a few limited number of legal templates. And if you cannot use a template, then what you got to do? You got to generate a no-op. Okay, so let's look at again the same example and let's see how we can generate it using templates. What you got here is again all those instructions, active instructions W00, W02 and so on. And we want to map them into this VLIW long instruction and generate these no-ops automatically. And then we also want to use these templates and map on these other instructions W12 and W14 onto yet another VLIW instruction that follows this. All this is taking place in the instruction buffer. Note that this is not at the point of decoding. This is at the point of generating the instruction before it goes inside the processor. The instruction is fetched from the instruction cache, the way it looks like here, and it is generated using these templates, and it is expanded. It looks like this, and then it goes into the decode unit. Let us take a look at how the templates look like and how they operate to map these instructions. So we got a template 0 over here, which looks like this. What is it showing? It's showing that map the instruction at the place 0 to the place 0 in the generated instructions. So that's why it takes this and maps this as the first instruction. 0 is the first position in the generated instruction, and 0 is the first position in the instruction that are following this template. Next it says the instruction which is sitting at the position 1, which is over here, 02, gets mapped out the position 2 in the generated instruction. So this instruction which is sitting at the position 1 after the template gets mapped on to the position 2 in the generated instruction. This is the position 0 in the generated instruction. This is 1 and this is 2. The third part of the template says take an instruction which is sitting at the position 2 after following it and map it on to the position 5 in the generated instruction. Where is the position 5 in the generated instruction? It's over here. This is position 0, this is 1, this is 2, this is 3, this is 4, and this is 5, wherein this instruction is mapped. Well, this is a simple small template, but are we done yet? No, because we still have some other instructions which are occupying this VLIW instruction. So how does that work? Well, there is a special procedure or a special template called chain. What that template says is something very, very simple. It says that continue this particular mapping to the same VLIW instruction that you are generating. We are not done yet. That's all it says. So continuing this process, now we encounter template 1. What does the template 1 says? Template 1 says whatever instruction is sitting at position 0 following it, which is over here, W06, now should go to the position 6 in the same VLIW instruction we were generating. So that's why this W06 is taken and it's put over here as per the template. Finally, we have instruction which is sitting at position 1 after the template. So this 1 is telling us it's a relative offset with regard to the template. Take that particular instruction and put it at position 7 in the generated VLIW instruction. Now it says that this completes this VLIW instruction, so we use a special word which is called as SEQ, which says that now try to generate the next VLIW instruction. And so what happens after that? Again, we go to the template and we find out template 2 here. What is template 2 doing? Template 2 is going to take that instruction which is at W14 and it is going to now map that on to a particular position given by the template, which is at the position 3. Having seen many different kinds of encoding schemes, now let's answer the last question, which is very, very, very important. How does encoding work with the instruction set extensions? By the way, what is an instruction set extension? As you know, instruction sets get modified with new instructions being added all the time. A great example is SSE extension or MMX instruction with the x86. Many encoding schemes therefore have to worry about extensions, and typically they leave room for future extensions. For example, in RISC, you reserve typically some opcodes or sub-opcodes for future instructions that may get added to the instruction set. In CISC, typically you extend an instruction by using some prefixes or mode bits which manipulate the instruction to do something different as per the extension. However, some extensions such as ISA extensions, which are a little bit more dramatic, can be a problem, because if the implementation is exposed through the ISA, then the new versions of software may not work. In certain cases, the old processor may still be able to deal with the new extended instruction sets. How? A new microcode may be loaded to emulate the instructions. Or in certain cases, the extended instruction can trigger an exception and can be rejected. So the real question is, what kind of extensions are possible in VLIW and how can they affect the different encodings? Typically, the VLIW, since it exposes the implementation, the extensions are quite rare. However, certain instructions are still feasible in terms of adding certain modes of operations, and those could be easily implemented by using the prefixes and so on, same as in the case of CISC. Now that you have finished this lesson, you should be able to answer the questions I posed in the introduction. What is ISA? What are the design decisions that need to be considered when choosing an ISA? And finally, what is unique about ISAs for embedded processors?